Physical distancing is one of the most effective measures for limiting the spreading of the COVID-19 disease. In this context, smartphones can be particularly useful for increasing the awareness of people about their closeness to other individuals. Exposure notification is a well-known service made by Google and Apple for detecting the close interaction between users. Exposure notification relies on Bluetooth Low Energy, and it has been used in several applications produced by health authorities for tracing the contacts of infected people. Now, the distance d between a couple of smartphones can be estimated by using the received signal strength indicator. In the slide, we can see the relationship between the received signal strength indicator and the distance between the devices. In this relationship, PTX is the transmission power, GTX and GRX are the antenna gains at the receiver and the transmitter, C is the speed of light, F is the frequency, and N is the path loss coefficient. That is a coefficient that depends on the environment. So the main problem is that an accurate distance estimation requires an accurate value of n. And as mentioned, n strongly depends on the surrounding environment. The reason is that obstacles, walls, furniture, materials all have an impact on the value of n. Our approach is to use the sensors available on common smartphones to automatically detect if the user is indoors or outdoors. And then this information is used to recognize users that are too close or at a safe distance with improved accuracy compared to an approach that does not take into account the environment where people are. Here we have an overview of the method. So first of all, the sensors available on common smartphones are used to collect information about the surrounding environment. This information is given as an input to a machine learning based classifier that produces as an output the current environment, that is indoor or outdoor. So we have just two classes, indoor and outdoor. Depending on the detected environment, a specific threshold is selected. So we have a first threshold S in for indoor environments and S out for outdoor environments. Then, when the distance between two devices has to be computed, this is done by comparing the received signal strength indicator values with the specific threshold. Specific, where specific means depending on the type of the environment, so indoor or outdoor. To this purpose, we used some commonly available sensors like the light sensor, the proximity sensor, the GPS unit, the Wi-Fi and Bluetooth transceivers, and also the activity sensor provided by the Android operating system. Light can be useful because indoor and outdoor environments are characterized by different levels of light. The proximity sensor can be useful for understanding if the device is in a pocket or in a backpack. The GPS unit is useful because indoors the signal received from satellites is generally weaker. Similarly, in indoor environment, Wi-Fi and Bluetooth signals are different from the outdoor ones. In this case, they are generally more abundant and stronger. There are also a number of categorical features like the daylight or the user activity. In this case, the features have been one-hot encoded. So we obtained a total number of features equal to 21. Here we can see the structure of the classification system. It has been implemented as an Android library. It is based on a TensorFlow-Lite model, and also the last indoor or outdoor status produced by the library and having a confidence greater than a configurable threshold is available to applications so that it can be easily retrieved, okay, because it is recent information. We performed an experimental evaluation of the method. So first of all, we collected some data. This has been done using an auxiliary application. The application was used for 2 days by 4 volunteers. The volunteers had to manually trigger the transitions between indoor and outdoor environments to collect the ground truth label. And it is important to notice that the test set is made of completely new data. So it is separated from the one included in the train set. We trained the model using the training set, and then we evaluated the model on the test set, obtaining an accuracy of approximately 59%, so not particularly good. And the reason is that the training set was built using the data collected by 3 volunteers, but the test set was made with the data collected by the 4th volunteer. So we repeated the training phase, now including also 25% of the data collected by the 4th volunteer, and the accuracy increased to approximately 93%. So there is a lesson that can be learned, that is in the detection of indoor-outdoor environments. It is important to include in the training phase some information about the specific environment where the system is going to operate. Then we evaluated the benefits of adaptation. To this purpose, we collected a number of samples of the received signal strength indicator at different distances, and this has been done both in indoor and outdoor environments. Then we used the average value of the received signal strength indicator at 1 meter of distance to define the threshold S. And then we evaluated the accuracy of the system, defined as the percentage of samples collected with a distance below 1 meter and samples that were characterized by an RSSI value higher than S as expected. Here we can see the results both in indoor and outdoor environments. As you can see, the dashed line that represents the value of S has a different value for indoor and outdoor environments. Okay? In indoor environments, it's a bit higher. Now, if we use the value of S computed by using the data coming from the indoor environment as in, we obtain an indoor accuracy of 91% and an outdoor accuracy of 72%. On the contrary, if the threshold is defined using the values collected in outdoor environments as out, we obtain an indoor accuracy of 79% and an outdoor accuracy of 93%. Obviously, if we use a different threshold for indoor and outdoor environments, the accuracy is higher, with an indoor value of 91% and an outdoor value of 93%. So overall, we can say that adaptation improves the accuracy of 79%. We also carried out a small comparison between ultra-wideband and Bluetooth Low Energy to understand which is the difference between the two technologies in estimating the distance. So we ran a number of experiments using a development kit made by Decawave. The kit is a MDEC 1001, which uses an IEEE standard for communication. And as you can see from the results, ultra-wideband is generally more stable in estimating the distance, and also in the end more accurate than Bluetooth, especially when the distance gets larger, as you can see in this picture. So, to conclude, we can say that methods for automatically recognizing the environment where the users are located, that is indoor or outdoor, can be helpful to improve the accuracy of the distance estimation process, in particular to understand if the distance is safe or not. We can also say that the knowledge about the amount of time spent indoor can be information also useful for other purposes. For instance, for evaluating the risks of the user, as it is well known that staying indoor is generally more risky than staying outdoor. And finally, the accuracy that can be obtained using Bluetooth Low Energy is in generally lower than the one obtained by means of ultra-wideband. But we also have to say that today the number of devices equipped with ultra-wideband transceivers is quite small. So today Bluetooth Low Energy represents the technology of choice if we want to provide an implementation that is compatible with the majority of devices.